Hi, in this video, we'll learn about 7 types of files supported on Linux operating system. Well, the 7 file types which I'm going to talk about is not specific to Linux. This is the standard file types found on most POSIX compliant environments. When I use the word POSIX compliant, I would say all Unix and Unix-like operating systems support these 7 file types. What are they basically? Well, first of all, I could tell you the first 3 file types represent data stored on persistent media generally. These are, first one I would say is regular files. When I use the word regular files, these files represent some data that seems to be persistent. I use the word seems to be because on Linux, you can have files sitting in pseudo file systems which make us believe that the data is actually persistent, but in reality they are not. Let's not focus on that. To know more, just wait for my video on proc file system and sysfs or the pseudo file systems on Linux. But for now, it is suffice to say, as a normal user, you will assume that when you open these files, you read some stream of data. Now, these are the files that we create, like text files, C source code, shell script, Python programs, or any files that we create, or any programs that get generated by the compilers or linkers, like the executable binaries, or some other tools that generate images. So all the files that we normally deal with on a day-to-day basis, I could generally classify them as regular files. If you come from other operating system background like Windows, you might say file types are either .exe files and .com files and .dll files, .txt files, and so on. You talk about file types based on file extension, but on Linux or on most Unixes, the extensions don't really matter. And the underlying file system or the kernel side, kernel space, all files are alike. Whether the file contains textual data or it contains binary data, they are not differentiated by the large part of the kernel and also by the file system drivers within the kernel. So just to give you an example on how to create regular files, I'm sure many of you do know, one of the very common ways to create a regular file is by using a text editor. So if you want to create your own regular file, you could just use your favorite text editor. I'm using Nano this time. You could use Vim, you could use Emacs, you could use any editor of your choice. If you're using a graphical user interface, you could also use gedit or Kate or Kedit, you name it. There are so many editors on Linux. For now, I'm going to use Nano and I'm just going to say a.txt, and I can just put some message in here. This is this file. This is line 2 of test file. This is another line in test file. And this is the last line in test file. I can just put in a bunch of data here. It could be normal text. It could be source code of any programming language of a choice or shell script or anything as such. So anything that's human readable and human written, right? This is a text file. I could actually save this. I could actually say, okay, I could Control X, Y to save this file. So this, when you run ls command normally, when you say ls -l, ls command will list all files as it is. But when you use ls with long listing on most Linuxes, I mean all Linuxes, you can see there are a lot of details being printed in here. Amongst them, the first series of characters represent 2 things. The file types, that's the first character that you see here, represent the file type, and the rest all characters represent the file permission bits. The file type is what is relevant for this particular video right now. I'll talk about file permissions in the coming video. But for now, if you see a hyphen as a first character, you could assume it's a regular file. That means this contains raw data of whatever size that is denoted in here, this particular field. So there are 117 bytes worth data in a.txt, which you can read by using cat a.txt. You can edit them. This could be a normal text file. It could be a source that got compiled. For example, if I write a C program by using nano hello.c, don't worry about all the C syntax for now. If you don't know C programming, don't worry about it. I'm just going to create a program that will just get compiled to show you what a binary file looks like. So if I just going to set it on 0 in this case and save this file. So now when you run ls -l, you can see hello.c is also a regular file. If you see a hyphen in here, and this file, you do a cat hello.c, you can see it does print the C source that I just typed in the text editor. You can compile this if you have a C compiler installed. If you have installed C compiler, you could use cc command. There's a shortcut to access the C compiler engine, which could be the LLVM Clang compiler, or it could also be the GCC compiler. These are the most commonly available compilers on Linux ecosystem. So I can actually say cc hello.c -o hello. This will compile this program hello.c and also finally link it to create a final binary, which is a program by name hello. This program binary has execute permission. When you say X here, this means execute bits are turned on by default. This is an executable binary. In fact, the size is quite large, but you can still see it's a regular file. It is not treated as a separate file type. The kernel does not really differentiate between the file a.txt, nor does differentiate between the file called hello. It's only for our understanding that we know that this is a text file and this we should know is a binary file. So if you just do a cat hello, you might get some ASCII garbage. You're warned, if you type in some of these binary files, sometimes your terminal can get garbage. Your terminal settings might actually get messed up, because a couple of these binary strings that you see here, the binary data, could accidentally become terminal control sequences, which can sort of change the terminal's character set and all that. So if you see after you catch some binary data, and when you type something on the keyboard, if you don't see the characters as you expected, then you might want to type in this command. This is a digression, sorry about this. So you can just say tput reset. This command is to reset a terminal, just in case you accidentally printed some binary data, like a binary file, and your terminal got completely messed up. Blindly type this command, tput space reset. Right? Okay. Anyways, coming back, I told you binary files are also regular files. It could be images or audio files, video files, you can name it. So all of these PDF documents, compressed archives, all of these are categorized as regular files on Linux. Then there's another file type, and that file type, I should tell you, is a directory. Directory is a Unix terminology for what we know as folders. In the Windows world, we use this term called folders. Folders or directory mean the same thing. A directory is a special file type which will host other files and directories. This gives you a complete hierarchical nature to the file system. So back in the days, before directories existed, you only have files on a tape or any kind of storage media, and all the files are just one space, right? You can't categorize them. You cannot say that these files belong to this particular category, this set of files belong to another category. So if you don't have this kind of categorization of files, one of the earliest ways to do that is creating hierarchical directories. So to create a directory, of course, you know the command to use is mkdir. If you don't know this, there's a command to create a directory. So mkdir command uses a special system call called mkdir system call, make directory system call, instructing the kernel or the file system driver in the kernel to create a folder in the path that you denote. Right now, my current working directory is this. pwd shows up that I'm in this particular directory structure. All of your Linux file systems start with a root directory. There's no drive letters in Linux. More about Linux file systems in the later point in time, but just know that all Linux and Unix based operating systems start with something called as root folder, which stands as root file system. So which drive or which partition does root folder belong to depends on one of the boot parameters passed to the kernel. While booting the kernel, you will say, okay, use this partition or use this storage space as the root file system. This passed by using root is equal to parameter normally while booting the kernel by the bootloader, and that storage space is treated as the root directory. What about if you want to access other drives? You need to mount them by using the mount command. We have this concept called mount points. That's a different topic for discussion. But now, within the root directory, there is a folder called home. When I use a folder or directory interchangeably, I'm meaning the same thing. Just note this. So under home directory, there is another subdirectory called Moonranger. This happens to be my user's home directory. Perhaps I've logged in as a user by this name. And under this, you have training. Under training, you have another folder called Linux Fundamentals, which I just created for this particular video. Now, in this particular folder structure, in this directory hierarchy, when I now say ls, I don't give any argument. By default, it shows the contents of the current directory. If I want to create a new directory in here, I can say mkdir and I can just say new folder. And when I say ls, you can see new folder that appears here. You should also note that ls command in many Linux distributions print output in colorized format. But some distros, they may not do that. In fact, there's a reason behind it. By default, ls is aliased to, in my machine, is aliased to ls minus capital F minus minus color is equal to auto. If I don't have this alias, the output of ls command will look very bland. That's what you will see in many Unixes. If you've been using a macOS, for example, and a macOS by default ls output might look like this, very bland. You might want to try ls minus minus color to get colorized output. When you use a minus F switch, minus capital F switch, it'll also add some hint based on the file type and the file permissions. The file has an execute permission, it ends with an asterisk. If the file type is a folder, it ends with a / Just a quick hint. This feature exists in all Unixes, not just Linux. It's a standard Unix feature. You can simply use ls minus F in most Unix based environment, whether it's FreeBSD or NetBSD, macOS, you name it. All Unix and Unix based operating systems support this feature. But this minus minus color option is a special feature supported by ls command that is bundled with GNU core utils. If you don't find this minus minus color switch not working on your environment, it's very likely that you're not using GNU core utils package, which provides ls command. So you might want to check up. I've seen on platforms like macOS terminal in the early days. I've not used macOS in the recent versions, but yeah, I would say the macOS that existed about 6-7 years ago doesn't provide GNU core utils. Doesn't provide them even now. But remember, instead of minus minus color, you would have to say minus capital G there. Oh, minus capital G doesn't work on Linux, but it'll work on macOS. Maybe if I had booted my macOS, I would have shown you that, but okay, I don't have the time for doing that right now. But just try it out. If you're using macOS, you would use minus minus capital F and capital G. You can actually combine them. You can actually say ls minus FG like this. This works on FreeBSD shell and also on macOS. So okay, coming back, I told you about the file type. I told you what a directory is. I created a directory called new folder. I can change to a directory by using cd new folder. The cd command will use a special system call known as change directory or chdir system call to change the current working directory. Now if you type pwd to get the current working directory, it shows it is a new folder. What it means is that most commands that take path as an argument, when you pass them a path without the /, it'll assume related to the current directory. So when I say ls, it shows contents of current directory right now, which is empty. I can say cd ... to go back to one folder up, and you can just see the current directory now. So folders are used to host files inside them and subfolders inside them in a hierarchical manner. So they give this entire hierarchical categorization of files in your file system, right? That's how they are. Think of folders are very similar to compartments in your drawer or a cupboard. So you open up a cupboard or a store well or a shelf, and you find compartments inside them. In each compartment you categorize them, and you can have sub compartments inside them. That hierarchy is what folders represent. It's nothing new. In Linux, it's been there in almost all the mainstream operating systems that you've been using. On Windows, you see the folders as an icon. Here, you see them in the command line this way. But this is treated as a separate file type by the Linux system, right? Another file type exists on Linux, which is not popular on non-Unix environments like Windows, for example. There's an equivalent of that in Windows, but it's implemented differently. And this is called as a symlink. Symlink is also called as soft links, or also known as symbolic link. Symlinks are used to create shortcuts. Symlinks are used to create shortcuts for different folders. So if you're using a symlink, the reason why you use that is because you have a long path and you want to reach out to the path by using a shortcut. You can create a symlink for it. There are lots and lots of uses for symlinks. So the way you create a symlink is you can actually say ln command and a -s switch. This is very important. In the traditional Unixes, there used to be a concept called hard link, which exists even today. Linux maintains legacy compatibility with all the traditional Unix features, so hard link support does exist on Linux. But let me tell you in summary, there's absolutely no reason to use hard links on a modern Linux system. So avoid using hard links. Hard links create more problems if you use them than solve them, right? Getting rid of the original file is going to be a nightmare, and hard links have lots of limitations. So I'm going to talk about the hard links versus soft links in a separate video. It demands a separate video to cover that. So I'm not going to be focusing more on it. To summarize, just use soft links. There's absolutely no need for hard links. Hard links are a legacy feature just being maintained for backward compatibility on modern Linux right now to be POSIX and legacy Unix compatible. But for all practical purposes, if you're going to be creating a shortcut to some path, you'd want to use a symlink, and that's done by using ln with a -s switch. There are certain Linux distributions that provides a shortcut for that. It's called a symlink itself. You could simply use a command called symlink to create a symbolic link, but then just remember the command ln -s. -s indicates create a symbolic link to where. I can say create a symlink for some long location. Let's say /user local. On my machine, I have user local src linux-stable, this folder. I'm going to create this as Linux kernel. So right now, you can see a file called an entry called Linux kernel is shown up when you run ls command. When you in fact say ls -F, symlinks are shown with a @ at the end. Folders with /, symlinks end with @. If you enable colorization by using ls -color, you can see symlinks could be colored a little differently. This is a very common coloring scheme I've seen in most Linux distributions, but some Linux distributions might work a little differently, so you might want to check it out. So they're colored differently, and what is it basically? If I now just say instead of going to a folder called user local src /linux-stable, it's a long path. Instead of reaching to this folder and seeing the contents this way, I could actually run it another way as cd- to go to the previous directory. If you want to go to the last directory, going back in history, it's a cd space hyphen in all the modern Linux shells, bash or z shell, for example. I'm using z shell in here, so this works even for bash shell. So now if I just say cd linux_kernel, is pretty much the same as going to user local src linux stable. So that's a path. I've created another alias or a symbolic link, a link to another path, right? A shortcut to another path. So this shortcut is called Linux kernel. I can just simply say cd Linux kernel and I see the same contents. The main use of symlink is this, creating a shortcut to long paths. It's also used for creating aliases to some certain files. On a typical Linux system, you'll find symlinks to maintain backward compatibility features. For example, on many modern Linux systems, you can see that when you see ls /, that's a root directory. Okay, I'll use ls -F -color for convenience because I unaliased it. In many modern Linux desktops and modern Linux systems, you might very well see that bin is a symlink, /bin that is a symlink, /sbin is a symlink, /lib. So if you want to see what they point to, you can also use ls -l switch, the long listed, and -f. You can say bin points to user bin folder, lib points to user lib folder. This bin and lib and all these folders exist for legacy compatibility. The shortcuts exist for legacy compatibility because certain applications or certain programs would expect for existence of bin folder, /bin folder, though it is not really required on a modern Linux system. Historical reasoning, in the early days of Linux, maybe if you use Linux maybe about 12 years ago, I will say Linux before 2010, right? 2010. During a point in time, the /bin folder was meant for hosting minimal program binaries required for booting the system. So minimal program binaries required for booting the system is hosted in /bin folder. The /user bin folder, on the other hand, used to contain program binaries for almost every software package that you install. Yeah, there used to be some more confusing folders like /user x11r6 bin and so on for graphical user interface programs. Command line programs were in the user bin. It used to be that way. Those were days when people had multiple partitions or multiple hard drives, where they would want to keep the root file system in a separate hard drive, and the /usr was maintained in a separate hard drive that will be mounted for managing packages and so on, right? So they used to be maintained in different file systems. Today, with hard disk space becoming cheaper and hard disk capacity becoming larger, in maintaining multiple partitions and multiple hard drives is no longer very intuitive or it's not very productive. So you could easily get a one big 2 terabyte or 4 terabyte hard drive as a commodity these days. So having multiple hard drives is generally not recommended in such cases. So you'll put everything in a single partition. So having separate folder called /bin, separate folder called /user/bin, figuring out what binary should go there, what binary should go in this other folder was a big nightmare for distribution vendors. So they came to a consensus. All program binaries now are consolidated under /user/bin. All program binaries, and the bin folder exists as a shortcut to reach to this folder. So even the minimalistic binaries that was required for system booting is there here. Plus all the other program binaries based on what all software package that you install is in this location. The same rules apply for lib folder. The /lib folder is to contain only the standard C library and the bare minimal libraries required for booting the system. Which is used by the programs required for booting the system. But now it's all consolidated in user lib folder, and lib now exists merely as symlink. Not only that, you'll find symlinks in other places on Linux, like say /user/lib. You go to the user lib folder itself. Let me use ls -- color -f. You can very well see a lot of these .so files. You can see there's all .so.0, .so.0, all the symbolic links. Symbolic links to what? This particular entry would be a symlink to this one. This entry could be a symlink to this one. These .so files are also called as shared objects on Linux, and these are just regular files which are nothing but dynamically linkable libraries. What you call as DLL files or DLLs on Windows is called as shared object on Linux environment. It's not just on Linux. I think this .so notation is found on Solaris and many other Unix-based operating systems. So Linux just followed that particular trend. So these shared objects are generally linked with program binaries. So if I have a program binary that's linked with a particular shared object, but the library writer, the libraries comes in a separate package, the software that's using the libraries comes in a separate package. They're two different software. For example, it's possible that the standard C library is maintained by some team, the glibc maintainer team, and I have written my own application using the standard C library, which comes from glibc. I have linked my program with a particular version of glibc, but later on the glibc team have come out with a bug fix release with a newer version. Is their newer version compatible with my existing program? That compatibility linkage is provided by these symlinks. Any program that's linked with this particular shared object will work with this version if necessary. Right? That's how they are. You can see this .so.4. This .4.1 could be a convention to indicate it's a bug fix release or a feature enhancement release, which is not going to break backward compatibility, right, with whatever program is dependent on version 4 of this libogdi library. So symlinks are used mostly for this kind of maintenance purposes, right? You'll find them in library folders. These days you find in many locations. You might also find symlinks in /etc folder, where maybe a legacy application or legacy program was expecting a configuration file in a particular location, but now you move the location elsewhere, but you don't want to break that program. So you create a shortcut for the older path that the program was depending on. So that's one of the use case for symlink. To create a symlink, I told you, to summarize, to create a symlink, you simply use ln -s and then provide a path to a folder or a file to which you want to create a symlink. So let's say I want to create a symlink this time to /etc/password, and then I say I'll say p.txt. This p.txt is a shortcut to a file /etc/password. Should note that symlinks are a special file type. They're shown with a L character when you look it up in the beginning, right? It is shown with the L character in here. And when you use ls-l, they'll also tell you where they really point to. But it should also tell you that for sake of shell scripting or sake of automation, if you know that the file that you're looking for is a symbolic link and you want to find out the file that the symbolic link points to, it is suggested that you use a command called readlink instead. Readlink reads the contents of symbolic link to see where it points to. You see that? Readlink p.txt, it points to /etc/password. If I say readlink Linux kernel, it points to user local src Linux table. Well, at this point, I should tell you that there are a lot of interesting questions that I could actually ask about symlinks as an interviewer. So if you're going to be applying for a job interview on Linux, you could expect a lot of questions coming from the concept of hard links and symlinks. So that's why I will create another video specifically on hard links versus symbolic link. So wait for that. But for now, just know what is the use case for symlink. The main use case is to create a shortcut to an existing path, some other path. Oh, not really existing path, to some other path. It is perfectly okay to also create a symlink to a path that is non-existent. Let me tell you that. These are called as broken links. So I'll show you what happens when you do that. I can actually say ln minus s. This time I'm just going to say, testfile.txt and to t.txt. What I'm really trying to do is that create a symbolic link called t.txt, which is supposed to point to a file called testfile.txt in the current directory because it's a relative path. But when I do this, let's say ls minus l, it does indeed create a symbolic link called t.txt, but what does it point to? Testfile.txt. You can see that this path does not start with a /, so it's a relative path. It is in the current directory. So if I do a cat t.txt, what happens? It will tell you no such file or directory. This is a very peculiar use case. You check for existence of a file. It says the file exists. The environment says the file exists. The shell says the file exists. And then you go and open the file by using any commands. You get this error called no such file or directory. You might be dealing with what we know as a broken link. So to see what exactly to make this work, let's say I could actually create a file. I can create a file now. This time I'll say cat greater than testfile.txt and say this is a sample test file. I save it. Now if I just say cat t.txt, it works. Broken links are links that point to a path that is non-existent. Well, that's not a bug, it's a feature. Okay, so it just says that there's a link, but this link actually represents a path, but the path does not exist. The path might exist in the future, or for now temporarily is non-existent. It's perfectly okay to have that, right? So this is what you should know about symbolic links. So in the ls command, you will see symbolic links listed with a small l, folders with a small d. You can see the small d here to represent a folder or directory. Directories show up with a small d, the file type, and the hyphen indicates regular files, right? The first cat that you see here. Now these three file types I told you are file types that correspond to data that we really care about. Now there are four more types of files. And what are those four types? We call them as special files. The special file types, the fourth one I should talk about is a character special file, then block special file. These two file types can be called as device files. And then we have another category, we call them as IPC files. And these are name pipes, also called as FIFO files. FIFO files or pipe file all mean the same thing. And you can also find Unix domain sockets. Oh, I'm recording the video when there's rain outside and there's a storm. So sorry about the thunderstorm if you're able to hear that. Sorry about that. So kind of not in my control. Yeah, nature has its ways in my city. Right. So Unix domain sockets, also called as socket files. These two file types, I will cover them in another separate video in great depth. I talk about devices and how Unix or Linux treats devices, files and all that. But in summary, I should tell you that this is a feature that's not specific to Linux. It has evolved this from traditional Unix. In Unix, most devices are visualized as files. And you'll find these files in /dev folder. You'll find a lot of them in the /dev folder. You see when I say ls minus l /dev, you'll see many of these files start with a character called C. These are called as character device files or character special file. These files are representative of what we know as character devices. And if you just scroll up a bit on my machine, You'll also see certain files that start with a small b here. You can see the files that start with a b. These are block special files or representative of block device files. So the file names like SDA, SDA1, SDB, SDB1, all of these are block device files. In summary, the block device files are created to represent storage media. If you want to access any kind of persistent storage media on a Unix environment and all the modern Linuxes, you represent them with a block device file. So on my machine, I have a couple of hard drives connected. I have this SDA1 happens to be one of the internal hard drive. SDB happens to be another internal hard drive. SDA is the internal hard drive, and SDA1 is a partition in that hard drive. SDB is another hard drive, and this happens to be a partition in that hard drive. So you can see all these two hard drives are represented as SD and SDB, each of them having one partition each. I also have a couple of devices which are the NVMe data drives, the NVMe SSD storage. You can see this NVMe 0 is NVMe 0 N1 is one block device, NVMe 0 N1 P1, this partition 1, partition 2, partition 3, each partition shown up as a block device. You can also see another NVMe device, NVMe 1, which is also seen as a block device. These block devices are used for representing all kinds of storage media, because storage media support two things: data persistence, and they support random access. You can access contents by doing random access on them, right? All storage media support random access. I mean, your normal storage media that we use. Even if I plug in a pen drive, that will be shown up as one of these SD kind of files, SDC or SDD. The naming conventions are just conventions that are followed in Linux just to make it intuitive for the developer and also for the power user. For most end users, they don't really care. In fact, the files that you see here in /dev, they were created manually using a command called mknode in the early days. But now, these days, these are all managed automatically by user space device manager called systemd, or the recent editions of Linux. When I say recent, I would say the last 8 years or so. It's all managed by the kernel. The kernel has this entire /dev folder is now a pseudo file system, a fake file system exposed by the kernel, pretty much like /proc. So when I'm writing a device driver and say it's a character device driver or a block device driver, I could actually specify what all devices to expose from within the kernel space by the driver. And those are shown up as files in a file system called as dev tempfs file system, and that is what is mounted under /dev. In the traditional Unix, and not traditional, many other Unixes even today, I would say, and very old versions of Linux, you might need to create these files manually using mknode command. This is done by the distribution installers and so on. Sometimes a power user might need to manually create files in here, but now it's all managed by the Linux ecosystem, the Linux kernel, and a couple of user space tools, so you don't have to worry about it, right? Just note, it is suffice to know that these are device files. What is specific about this? These files do not store any data. An attempt to open this file and write or read from this file will trigger callback handlers for the underlying device drivers. So when you try to open this particular file and try reading, you're trying to indicate to the underlying device driver to get data from the device. So data is fetched from device dynamically and given to the user land. So they don't represent persistent data all the time. They're all gateways to access devices. You might ask me, what is the significance between character device and block device? Then block device is totally meant for storage. They support two things: data persistence and random access. Character device, on the contrary, would support sequential I/O. They're designed generally for sequential I/O, but there are many character devices that don't do sequential I/O, that allows you to do random I/O. But one of the things is that they don't necessarily represent persistent storage. In summary, you cannot host a file system in them. You cannot mount them like a file system and use them, right? So this is a difference between character device and block device on Linux. I should also note that this difference is slowly getting thinned down in non-Linux environments, especially if you work on FreeBSD or macOS. You'll not find block devices anymore. You'll only see character devices. Even your storage media is all shown up as character devices in the latest editions of FreeBSD and the latest editions of macOS. Whereas Linux still has a clear demarcation to represent storage media as a block device, because there's a block I/O subsystem to manage all the block I/O transactions, and a lot of optimization happens in the kernel there, buffering, caching, and all that, read aheads. There are a lot of things that kernel does for optimizing storing data on storage media, reading data from storage media. Calculator device will not go through those those layers. They give you access to raw device, can get data raw from the device, either for read or write operations, right? In summary, these are two special files. In most cases, as a modern end user on Linux command line, you don't have to worry about creating these files. Suffice to know that these files must exist in /dev. You find these files anywhere outside the /dev folder, it's a chance that there's some kind of a security problem. You need to verify that. So because these files should not ideally exist under /dev folder unless you are the one who created it and you know what you're doing, right? So in a normal Linux system, all of these files, the device files, are confined under /dev folder. There are certain Linux distributions that even which are hardened distributions, which will not let you create device files outside the /dev folder. They restrict you from doing that. But it's a security feature, because exposing device files anywhere can actually open up a lot of security loopholes for all these malicious users to exploit. So that's the reason why you have to look at this with caution, right? Anyways, I'll talk about devices and device files in another separate training, but just in this summary video, you just know what these are. The next two files I should talk about are IPC files, which is quite interesting for now. The first one of the IPC file is namepipes, which is the sixth file, right? Namepipes. Namepipes are used mainly for inter-process communication. One of the common use of namepipes is for communication between two different shell scripts. If you ever know, there's an IPC called pipe on all Unix environments, and we commonly use this in shell command lines. For example, I could say ls. ls command just lists what all files are there in the current directory, but it does not tell you how many files are there. Most commands are designed to just do one job and do it well. Keep it simple principle. It doesn't really tell you how many files exist in a directory. So if you find out how many files exist in a directory, you might want to run ls pipe wc. wc stands for word count, which will basically count number of words, number of characters, and number of lines passed on to a stream. For example, in this case, stand input. When you say Ctrl D to N, it tells you that so far I typed about 6 lines, 16 words. Totally, if you count the number of words are nothing but tokens separated by white spaces in here. There's 16 words and totally 169 characters. So when I run ls command, I can also use wc minus w to count number of words, or wc minus l to count number of lines. Now it will count number of lines this time. When I say ls pipe wc minus l, there's a more short way to find out how many files exist in a current directory. 9 files. You want to know how many files exist in /etc? You can say ls/etc, it shows a lot of contents. Against ls/etc pipe wc minus l will exactly tell you how many files exist in /etc, because it's counting number of lines. Yeah, some of you who are little power users might wonder, isn't this wrong? Because ls/etc is showing 3 different files in the same line, right? But here's an interesting fact about ls command. There are certain commands that know whether the output is a terminal or output is a non-terminal, like a pipe. See, if I say ls/etc, it shows up in a very nice format with multiple columns, right? You can see 4 columns with data being printed. It figures out the terminal dimension and figures out that you can put 4 columns worth file listing, nicely formatted for human readability. But if I say ls/etc pipe, I'm just going to use cat command only. It's called as yet another useless use of cat. Okay, but just to demonstrate what it does, I'm sending ls output through a pipeline. I'm connecting the output of ls command to the input of cat command. Cat reads from std in, writes to std out. ls command prints contents on std out. I'm connecting the output of ls to input of cat. That's how pipelines are connected. You see, it doesn't show in multiple columns. So whenever ls output is sent over a pipe, ls prints output in a very raw format as possible. It knows it's not a human being who's reading it, it's another program. It becomes more program friendly. This is an interesting feature with many tools on Unix and Linux. So when I say ls/etc minus wc minus l, it tells you totally how many files exist in /etc. Alright, I digress, but I just told you about file types, right? I told you about I talked about pipes. So this is a pipe. This is an example of a pipe, and this pipe is called as an anonymous pipe. When you use a pipe symbol in here, you're actually telling the shell to create an anonymous pipe, create two child processes. One child process runs ls command, another child process runs wc, and you're connecting the standard output of ls command to the standard input of wc, so these two children can communicate with each other. This is an IPC created by the parent, that's a shell, so the two children can communicate. So for creating anonymous pipe, the process must be in a single family. Parent creates it, two child can communicate. Parent creates it, and parent and child can communicate. It must be in a family, right? But what if I have a program running in here, like say ls/etc here, but I want the output of it to be processed in another terminal altogether. Let me bring up another terminal here. Yeah, I have another terminal in here. I want the output to be processed by a program running on this terminal. I want to run wc command in this terminal. Now, this wc command and the ls command is not in the same immediate family. There's no common parent for them. The parent for the ls command would be a shell that's running in a separate terminal, which is its parent, and wc runs in a different shell instance, which has a different parent. So they're in two different families. Hierarchically, they will all come from a root called init, but they're two different subfamilies, right? They cannot see each other right now. They run in a sandbox. If you want to create a communication between processes that do not fall in the same family, you can use a name pipe. I'm going to show you an example for this. This time, I'm going to say ls, but in order to use a name pipe, we need to create this file. Okay, I'm going to create a special file here. I'm just going to say I'll just use alias ls is equal to ls minus color minus f, because I find this very, very convenient. So when I say ls, it's going to show in colors, and it's also going to show the special characters in here. In fact, with the colorized ls, when you look up contents or /dev, all device files are shown in a special color in my machine. Okay, most distributions show it either in yellow, some of them orange, or brown if you want to call it brown. So the names are sort of interchangeable. You'll see different people using different names for the same color, let's say, depending on what kind of terminal you're running. So you can see all of these are device files shown up in a different color. For now, I'm going to create a file, which is a special file, a FIFO. To create a FIFO, you say mkFIFO, and then say testdata.dat. The file name and the file extension does not matter. You can give anything that you want. I'm going to say ls-l. This is how you create a FIFO file. You see a small p here. All pipes or name pipes start with a small p. And you can see an entry here. And it ends with a pipe symbol. And use a ls minus capital F, by the way. And it's also shown in a slightly different color. It's not really yellow. I'm not sure what color is this. What do you call this color? You don't know. We just look it up in the color table, find out. Okay. So, but anyways, it's a different color, right? Some kind of a foreground background color, not very similar to what you find in /dev. It's bold yellow, but maybe this is a thin yellow, let's say, right? Looks yellow to me, but fine. But you can see this is what a named pipe is. An interesting fact about named pipe. I will say ls/etc greater than. If it's a test data.dat, greater than is to redirect the output of ls command to a file. If I redirect to a name pipe, it blocks the ls command. See, the ls command is blocked. It's not coming back to my shell prompt. How long? It'll be blocked until you go back and read it here. Here, if we say the same command, the same another shell, I'm the same folder. You can see this file called testdata.dat. The moment you say wc-l testdata.dat, that ls command's output is now sent to this particular wc-l, and it's able to read it. Now wc-l is able to process it and say there are 276 files. 276 lines from this particular file. Another intuitive use case I can show you is this. Let me just try to reduce the terminal size a bit. I want to keep one of the terminals on this side. Okay. I want to keep another terminal on this side. Two different terminals. They're in the same folder. So I'm just going to go to this terminal, the first terminal, and I'm going to type cat greater than, and I'll just type testdata.dat. And here I'm going to say in this terminal cat testdata.dat. Cat greater than is going to write to a file. This is going to read from the file. Now in the first terminal, I'm going to type a line and see what happens. You see some kind of a communication going on. This is what a pipe connection is, right? There's a pipeline connected from a program running and the shell running in this particular terminal to the shell running on this particular terminal, and the cat command is able to communicate amongst themselves. What if I bring up one more terminal? I think I have one more terminal open. Let me just use that. Reduce the size a bit. I'm going to keep this on this corner. I'll say cat test data.dat. So you can see this terminal and this terminal are actually opening the file for reading and trying to read data. In this terminal, it's going to redirect output to a file. What are the user types? So if I'm going to type a line, some lines go to one terminal, some lines go to another terminal. You see this? Basically, it's a one-to-many communication. When I say one-to-many communication, it's not really broadcasted. The message is not broadcasted. If I type one message in here, it's captured by one of the process running. If I type one more message, it might go to another process. You see this? The message is either sent to one process or another process. So when it's like, imagine in a classroom, I just throw a chocolate. The moment I throw a chocolate, one of you might hold the chocolate. Whoever gets a chocolate, he consumes it. It's basically a concept of producer-consumer. That's what a pipe is all about, right? So you have one producer, many consumers. What is consumed by one process on the pipe is not seen by the other consumer here. What is consumed by this consumer is not seen by this. So it's like one process reads data from that pipe, the other process will not be able to see it. So this is one of the important limitation of a pipe, and that's how it is. That's what a FIFO is, right? A FIFO is basically a name pipe, a pipe which is given with a name, a special file name. If you see this FIFO file on your Linux system, as you see, ls-l. Okay, let me just zoom this a bit right now. You see a pipe file like this, right? If you even run ls command without a -l switch, a pipe file might end with the pipe symbol if you use a -F switch, and it'll be colored a little differently. With the ls-l, it'll show up with a small p as a representation. So what have we learned so far? Regular files show up with a hyphen, right? Symbolic links show with a small l. Directories with a small d. Block devices with a small b. Character devices with a small c. You can create a block and character device by using mknode command. I will cover them in another video. For now, I'm just going to tell you that these are the other types of files. And you can create a FIFO file easily by using mkfifo. You can also create this pipe file by using mknode, but it's convenient to use mkfifo. You don't have to worry about extra switches. This is available by default on almost all Linux systems. So you can actually use mkfifo to create rather than using mknode. The last file type we talk about is Unix domain sockets. There are no straightforward Unix or Linux commands to create socket files. These Unix domain sockets are created when you create a socket using the socket API with the socket domain as af_unix and sock_stream, and then you bind the socket to a file. The act of binding the socket creates it. But one of the tricks to create a Unix domain socket is if you have a tool called NC. NC stands for netcat. This tool might not be there by default in many of your Linux environments. If it's not there, you can just install it by using sudo apt install. If you're using Ubuntu, apt install netcat. You can say netcat openbsd. Install this. Netcat and openbsd is a very common version of netcat. This tool is mostly useful for communicating over network sockets. Whether it's TCP socket, UDP socket, Unix domain sockets, you can use all kinds of socket-based communication. It is used alongside with Nmap for all this kind of security tests like penetration tests and so on. Okay, it's a tool used by all the security experts for pen test kind of operation. So yeah, it's a very simple tool. It's also used by programmers for testing network socket programs and all that. It's a very good tool for debugging network socket programs. Netcat has lots of switches. If you want to create a listener socket using netcat, you could say nc-l. But what kind of listener socket I want to create is I want to create a Unix domain socket. So I'll say capital U. I want to keep the socket to allow communication with multiple connections, multiple client connections. So I give a small, I'll also provide a small k. When I run this, and when I use a capital U, you need to also provide the file name, the socket file name. So let me call the socket file as test dot, test sock dot dat. This creates a socket file. To verify that, you go to another terminal, and if you just run ls this time, this is a socket file is shown in a very interesting pink color on my setup. And you can see it ends with an equal to sign if you use ls minus capital F switch. That's what my ls is alias to, right? If you run ls minus L, you can see that socket files start off with a small s switch. You can see small s character. You see this? Pipes with a small p, socket with a small s, right? So this is a listener socket I've created. Now in order to communicate to this, I can still use nc command in another terminal to create a connection socket. I'll do that in here. Let me reduce this terminal size a bit. Right. So here I'm just going to say nc and minus u. Create a connection socket to this Unix domain socket testsock.dat, and I can type in something. Sockets allow two-way communication. I mean, the difference between a pipe and a socket is pipes are generally half duplex. When one process writes, another process should read. When the other endpoint process writes, this the process must read. It's just half duplex. You cannot do both read and write operations simultaneously. It's like this: when you open a file, you open the file in read mode or write mode, or you can open a file in read-write mode. But if you're working with a pipe, either you can open in read mode or you can open in write mode, but you cannot open in read-write mode. So if you're opening read-write mode, it's going to fail. You cannot do both read and write simultaneously. That's the half duplex communication limitation. Sockets, on the other hand, are designed to support full duplex. Think of socket like two pipes. One pipe to communicate in one direction, and the pipe to communicate in another direction. So like two pipes communicating with each other, right? So two different processes. So it's like communicating using a walkie-talkie, where you talk, flip a switch, and you listen, right? You say talk and you say over and you listen back. So it's a flip switch to switch between talk and listen mode, whereas your normal mobile phones are supporting full duplex. Telephones are full duplex, right? That's the difference. So you can see the socket is supporting full duplex. So you can type something in here and that's visible on the server. You can type something on the server side and it's visible on the client. Happens. What happens if another client tries to connect? Let's say nc, and I'll use minus capital U, and I'll try test sock.dat. And just now I'll type in some message. I'll say just all A's, all B's, and all C's here. Nothing happens. It's not gone to the server. The server is busy with one client. When this client closes the connection by maybe the act of Control D or Control C in this case, then whatever message was sent by this client is sent to the server. The server is now communicating with another client. The main difference between a socket and a pipe is socket allows you to have many one-to-one communication channels. A typical client server architecture. You have a server that can cater to client 1, then it can cater to client 2, then it can cater to client 3, can cater to multiple clients. So the server listens for incoming connections from multiple clients, and each client can have its own session with the server. Right now the sessions are very sequential, but if you do programming, you can actually make the sessions more concurrent. You can have multiple clients communicating concurrently, and the server can flip between different clients by using a couple of IO concurrency mechanisms, whether it's be threads or be it IO multiplexing techniques, right? But what we should know is about the file type I talked about the sockets. So in summary, I told you about the 7 types of files. So what are they? So basically, if you just recollect, I told you regular files, directories, symlink, character special file, block special file, name pipes, Unix domain sockets. Let me also write here that regular files in the ls output, ls-l output, they're shown with a hyphen. Directories are shown up with a small d. Symbolic links with a small l. And the commands to create them. Regular files, any text, any editor or tool will do to create that creates a file. That creates a file. Directories are created by using mkdir, right? That's a very commonly used command. And for symbolic link, use ln-s. And the special file types, device files, you'll see them with a small c. And to create device files, you can use mknode command. Even for block device files, you could use mknode. I will talk about the ways to use mknode command and so on in another session when I talk about device files specifically, Linux device files, right? And you can also create a name pipe by using mknode, but it's suggested name pipes are shown with a small p in the ls-else output in the first scatter. You can create them by using mknode, but it's preferred to use mkfifo rather. And I showed you how to create a Unix domain socket. Unix domain sockets are shown up with a small s, and these are created mostly by, if you want to use a tool, use nc. That's basically netcat command. nc minus capital U or nc minus capital, you can say L, U, and K. These combinations. Create a listener socket, which is Unix domain socket, and keep the connection on. Keep the listener socket on after the client closes the connection to allow multiple clients to communicate. That's what this small k indicates. So all of these are the ways to create them. The final thing I should tell you is that the Unix domain sockets are used traditionally by X Windows system for interprocess communication. You can find a couple of Unix domain sockets. If you are lucky, you'll find them in /temp folder. Let me just find out if it's still there. Okay, there's a lot of files in my /temp folder. If you might find a file which used to be called .x11 Unix. Okay, I think this is now changed. It's all moved to maybe /run folder, I believe. Yeah, maybe. You can see docker.sock, snappd.sock. So all of these are Unix domain sockets. Many server applications would actually create a Unix domain socket allowing clients and other applications to communicate. Many services. In fact, traditionally the X Windows system also used to create a Unix domain socket under /temp /.x11-Unix. You'll find a file called x0 or x1. That's the socket file representing the X server communication mechanism. But the modern X Windows system on Ubuntu is migrated to not the original Xorg server, but we're using Wayland. So Wayland might not be using this Unix domain socket in that original location. That locations have changed. All right. So anyways, this is the video. I had to finish the video at this point. So I hope you understood all the 7 types of files on Linux and what are they mainly used for. In the further videos, I will dig onto each of these file types with more depth, mostly in dealing with the symbolic links and hard links, and also tell you about device files. Right? Thank you very much. Hope you find this video useful. If you do find this video useful, do comment. Do add some comments, so just give me some motivation to make more videos like this. Thank you very much. Hope to meet you all in future videos.